Hi everyone, thanks for coming. So today we're going to talk a little bit about how the Android framework monitors, processes, and triggers ANRs. So basically read through the source code of the Android OS, so you don't have to. So a little quick intro to myself. I'm a mobile architect at Embrace, so I work on our Android SDK and all of our other mobile SDKs like iOS and Unity. And Embrace is a mobile observability and analytics company that basically lets you see what a user's been doing for the entire session leading up to a crash or performance problem. And we've definitely spent a lot of time trying to figure out how to help customers reduce their ANR rates through what we think is a fairly unique approach to data gathering, but we'll cover that in more detail later. So first off, I just wanted to kind of set the scene and recap on why we actually care about ANRs. So this is the Google Play console bad behavior metric. So basically, you need to stay below this orange line, which is 0.47% of sessions having an ANR. And that can be really hard to do. So yeah, there's various reasons why you might be going above that orange line. But if you do go above that orange line, then it's basically a bad experience for users, but it's also hurting your business. So there's several consequences to that. You can have a lower Play Store ranking. So for example, you won't actually show up in organic searches on Google Play. So that can affect your customer acquisition. It's just generally a bad experience all round, and if the user basically experiences like a freezing app, they're far less likely to actually purchase something in your application. So from our experience, there's two main challenges that come with ANRs and actually being able to solve them. So those two main reasons are there's kind of limited data to solve an ANR. You get a stack trace if you're lucky, and that's usually about it. And we also find there's kind of a limited understanding of ANRs and thinking it's basically just the stack trace that is going to help you. So hopefully we can help with that second one. So just to go over the agenda for what this talk is going to cover. Firstly, we're going to go into what the current limitations are with what ANR data is actually captured. Secondly, we're going to talk about the different ways to actually access data on ANRs. So that might be on your local device or through monitoring solutions. And then we're going to take a little bit of a dive into the Android OS source code itself, telling you how ANRs are actually triggered and how the Android framework actually writes ANR trace data to disk. Finally, we're going to cover a little bit of how additional data can actually help you solve those ANRs. So let's start off with our first item, the current ANR data that's captured and its limitations. So firstly, I just want to kind of reiterate the difference between an ANR and a crash, which might seem obvious, but it's good to set the scene nonetheless. So usually a crash is effectively just going to terminate your app straight off, and it's fairly deterministic. If you've got a stack trace, you know more or less how to go and fix it. So in our example here, if the user goes to a checkout screen in your e-commerce app, there's some sort of bug in your checkout code, and that causes the app to crash. If you had an ANR, it's altogether a different experience for debugging that. There's so many things which could go wrong really in that checkout code, and it can be quite hard to debug that as a mobile engineer. You might have a heavy UI update. You might have a third-party SDK blocking the main thread, which is usually not something you can really know about. And all those things can basically contribute to ANRs. And they might not even happen on your own device because it's relatively high-powered compared to a user's low-end device. And another important thing to kind of touch on here is that there's a difference between deterministic behavior and non-deterministic behavior. A crash is basically deterministic. You're triggering a condition in your code, and it's pretty much always going to be the same. So it makes it a bit easier to reproduce. That's not always the case with ANRs. We've kind of tried to illustrate it with cars here. If you're lucky, you might get an ANR where the main thread is paused for like 20 seconds or something like that, or you've got a deadlock where two threads are waiting on each other. And in that case, the stat trace that Google gives you, that's okay, it's pretty useful. You can identify what the ANR was. There's another scenario, though, where you're just doing a lot on the main thread at the same time. So you maybe queued up like 20 different separate bits of work, and it might be non-deterministic, like depending on whether the user makes some network calls or not. And in that case, the stat trace provided by Google is not always deterministic, so you can't really tell what exactly is causing an ANR, because it's multiple things. So in terms of how the Android OS actually provides data, in our opinion, it basically provides it as though it were a crash, which works well for the sort of deadlock scenario, or where you're doing something you really shouldn't be on the main thread. It doesn't work so well for the second scenario, where you've got lots of little bits of work. So I can just run through this diagram. So basically, your app would be running normally, and then it might freeze because a user goes to a separate activity, for instance. During that period of the main thread being frozen, the user can't actually interact. And if they can't interact for a threshold, usually 5 seconds, but we'll cover that later, the Android OS will capture a stat trace. And at that point, the app can either get terminated by the user, or the user might choose to wait. So let's go over a little bit about how ANR data is actually captured by the Android OS. So this is kind of like a high-level principle that applies to most of the components in Android. That's services, activities, etc. But essentially, the Android OS always monitors the main thread from the background thread as soon as a component has work scheduled. And as soon as that work is scheduled, the monitor thread basically has a runnable set on it. And if the main thread doesn't complete execution within like 5 seconds, then the time threshold was exceeded, and the ANR data will effectively be captured by that monitor thread automatically executing the runnable. So if this happens like in a development environment, there's a few things you can access by pulling the trace file off your device. And honestly, this is kind of a best case scenario. So stat trace of a main thread, pretty much everyone will have seen that who's looked into debugging an ANR. There's also a bunch of extra information like memory information, CPU usage, and bits that Google basically use for their own metadata, which can be quite useful. In terms of like the data you can access in production, there's probably like 2 main solutions that we hear people using a lot. So that's Firebase Crashlytics and Google Play Console. In terms of the data they capture, they use different mechanisms as far as we can tell. So Firebase Crashlytics uses application exit info. That's basically recorded every time a process exits and is recorded from Android 11 onwards. Whereas Google Play Console, we think it uses the trace file actually recorded on the device, which is supported on older versions, but does tend to have a little bit of a delay actually showing up in Google Play Console. So the problem with this approach is it's kind of almost treating the symptom rather than looking at the root cause of finding out why your app froze. So typically there might be something happening in like the 1 second or 2 second mark, which is kicking off some work, and you just get to see the mess that was left behind from the stat trace at the end. We'll go over this in a bit more detail later. So let's talk a bit about how ANRs are actually triggered in all the different components on Android. So I think there's a common misconception that if the main thread is blocked for 5 seconds, then that means an ANR is going to be triggered. That's not always the case. It's actually quite different depending on which component you're in and what the conditions on the device are. So this kind of like summarizes the timings, and we'll go into these in a little bit more detail. But I just found this interesting. So this diagram kind of shows a very high level of how the Android OS basically schedules work in your app. So kind of a bit of a reminder. But the Android OS will call into your app to like display an activity, or it will invoke a broadcast receiver when there's some sort of system event. And if they take too long to respond, then you're basically going to trigger an ANR. So every time work is scheduled, that's on those yellow boxes, the Android framework basically kicks off a timer on a monitor thread. And if that threshold is exceeded, the Android OS doesn't get a chance to cancel that execution, and it automatically calls this class within Android called ANR helper app not responding. So let's go through the individual components and their timings in a little bit more detail. So an activity, basically you can get an ANR there if input dispatching takes more than 5 seconds. And this is where the kind of common misconception that an ANR takes 5 seconds comes from. So basically, just to recap input dispatch, if you touch or tap on your device or enter a keyboard, that's classified as an input event, and it gets put on a queue called the input dispatcher. That needs to get processed ASAP, basically, because if it's taking like a second or so, your device isn't going to feel responsive, and it's going to be a really frustrating experience. So effectively, to kind of combat this, if a main thread gets blocked for up to 5 seconds, and an input dispatch event has been queued, then the watchdog thread basically triggers an ANR. And the key point there is that the user actually needs to perform some input. Like, you can block the main thread for more than 5 seconds in an activity, and if the user hasn't interacted with the app, you don't get an ANR. And that's basically because the user is not actually going to be interacting with the device, so they haven't had a bad experience. So this diagram basically just summarizes that. So in our first example, the user's not actually interacted with a device at all. They've not tapped it. So the main thread does get blocked, and the monitor does get set, but the ANR basically gets discarded because the user didn't see anything, so it didn't happen. So it's like trees falling in a forest. With our second example, the main thread does get blocked, but the user taps on their device a little bit, and that does trigger an ANR. And this diagram effectively shows you what the Android OS is doing internally when work is scheduled in an activity. So let's start from the top. So the Android OS schedules work in your activity. You get some user input when the activity is displayed, maybe. And that user input gets put on the input dispatch queue. If that takes longer than 5 seconds to process, then the threshold is exceeded. And the Android OS is basically going to record a trace file, show a dialog, and then the user decides whether to kill your app or not. Next, let's cover a service. So that's basically something that performs long-running operations in the background. But there's a couple of different variations on that. So there's 2 places an ANR can trigger specifically in a service. Basically, if you've got a foreground service and you don't call start foreground in under 10 seconds, you get an ANR. And if you have a service that doesn't start or bind in under 20 seconds, or if you're in the background in under 200 seconds, then you'll also get an ANR. So the reason those thresholds differ a little bit is based on impact to the user, we believe, and basically CPU priorities. And this kind of summarizes the logic flow for the Android OS and how it handles that. So if you have a service and the process is in the foreground, you can get a threshold of 20 seconds in which you can start that service, or 200 if it's in the background. With a foreground service, it's 10 seconds. And if any of those thresholds are basically exceeded, you get an ANR. So this is the same sort of workflow for an activity. ANR trace file gets recorded, you get the dialog, and the user decides whether to kill your app or not. Next, let's cover a broadcast receiver. So basically, the threshold for this is 10 seconds in on-receive. So if you take longer than that, effectively you're always going to get an ANR. There are a couple of exceptions to this, mainly when the device is booting. So the reason being, when the device is booting, CPU is a pretty scarce resource, so there's a little bit more leniency there. And again, this diagram kind of summarizes what's happening. So if you take longer than 10 seconds in on-receive, the threshold gets exceeded, trace file gets recorded, and the ANR dialog shows up. Finally, let's cover a content provider. So this is probably a little less common as a component, but it's actually got quite an interesting condition in that there's only one ANR that can be triggered from a content provider specifically. And the condition for that is if you don't call getProvider MIME-type within 1 second. There's actually a really easy, concrete solution for avoiding ANRs within content providers, which is using the getProvider MIME-type async method. And again, this diagram just kind of illustrates how a content provider ANR works. So if you exceed that threshold of 1 second, you get the ANR trace file, the dialog shows up basically. It's the same code path between all those components. So now that you kind of know what the thresholds are for all the components, we can talk a little bit about how you actually trace the origin of an ANR. So all these components basically run on the main thread most of the time. And this leads to an interesting scenario where you can have multiple components basically starving the main thread and ANRs triggering from unexpected locations. So I think everyone here has probably experienced an ANR in some random activity that doesn't really do anything intensive. One of the reasons behind that is you might have something just before Google takes a stat trace doing something really intensive. So in our example here, you might get a broadcast receiver which takes several seconds to do something, and then an activity which performs something a little intensive but not too crazy, like loading an image. And depending on timings, if you take more than 5 seconds after an input event, then you can basically end up with a stat trace from the wrong component, which isn't really useful for debugging. This kind of illustrates what's happening with component overload. So using our metaphor of cars and being like heavy traffic. So you might have like dozens of components running on a thread at the same, running on the main thread at the same time. And those can all contribute to an ANR cumulatively, which can make it kind of hard if you're just getting a stat trace of 5 seconds. So that can vary depending on how the device is performing, what other apps are running, stuff like that. So we can recap a little bit about what the guidance is generally to try and avoid ANRs. So for instance, you can obviously not do network calls on the main thread. That's a definite no-no. And minimizing file operations and synchronization are also fairly common sense things, but can be tricky to actually implement in practice. One thing that we often spot is NDK code is a little bit of a blind spot. If you're writing files from within NDK code on the main thread, that will trigger an ANR regardless, but it can be a little bit harder to actually see. So now let's go on to how the Android framework itself actually collects data on ANRs. So this schematic basically shows you all the Android OS classes which are responsible for capturing an ANR. So we kind of covered the bit where the ANR thresholds are calculated for all the different components. So essentially, there's a common code path after that happens. So if an ANR has been triggered, the first class which gets called is ANR helper app not responding. That does a few things. So it basically writes a trace file to the data ANR traces. and also records a bunch of miscellaneous system events, which are used for internal metrics. Once that's happened, and the initial ANR data has actually been collected, the process record is updated, and that's basically just like an internal class which keeps track of whether a process is crashing or not behaving well. At that point, there's some further ANR data which is collected internally and more OS metrics, and then app errors is a class which is basically responsible for showing all the user interface of the famous ANR dialog. So then the system UI basically shows the dialog to a user, and they decide whether to let your app keep going or whether to terminate the process. There's a couple of exceptions to this rule where the ANR can get discarded by the Android framework. So if you've got an app with a debugger attached, if you want to debug your ANR, you won't actually get ANRs, as basically if you land on a breakpoint, you can pause execution and get them artificially. If a process is exiting or aborting, then obviously there's kind of no point reporting to the user that it's slow if it's just about to die. And finally, if the ANR is already in progress, also no point reporting that, the user already knows. One important thing I want to capture on with the bad behavior threshold is that there's a common perception that if you just load an app and interact with it a little bit, that counts as a session. That's not actually the case in terms of the Google Play's Android Vitals metrics. So, for example, if a user launches an app 5 times a day, you might expect that to equate to 5 sessions. So if you have an ANR happen in one of those sessions, you might say there's an ANR rate of 20. But that's not actually the case. Android Vitals calculates the session metric as the number of users who've used your app at any point during the day. And this can really throw off like session calculations and means you really don't have much room to play with ANRs in your app. So let's talk a little bit about how there are other approaches for like solving ANRs a little bit easier. So one approach is basically to sample the main thread and at a much earlier point and keep going until the ANR ends. So in this example here, the main thread is basically blocked, and at about 1 second in, we start sampling the main thread to grab a stack trace. And we think that this approach, which is what we use at Embrace, basically gets you the context of the ANR throughout the entire ANR. And you can kind of see how the main thread has been behaving through time. And coincidentally, if you do basically capture that information from about 1 second on, it will reveal some quite interesting things about how your app behaves. So ANRs are commonly seen as like 5 seconds of the main thread being blocked. But there's actually quite a lot of blockage on the main thread. These are some metrics which we pulled from our own internal data. And you can see that there's like a 2x times there's 2 times the amount of the main thread being blocked for 4 seconds, which is still a pretty bad user experience. You might not get an ANR in the Google Play console, but it still does affect your app. And it gets kind of progressively worse the lower your threshold goes. This can be also quite useful if you think about trying to actually reproduce an ANR. If you want a higher powered device than your users in, say, developing countries, you're not going to see the ANR basically because it'll happen so quickly on your own device. So I'd like to show you a flame graph. So this is basically the approach that we take at Embrace. We basically capture flame graphs of an ANR in production. And that kind of shows you how an ANR evolves over time. because you can see basically what the slowest methods are, and then you can prioritize fixing them instead of having to rely on that stat trace towards the end. So we can just cover how you would actually use a flame graph to debug that. So basically, step one of fixing an ANR, which might sound obvious, is basically finding the slowest method. You want to find the thing which is slowest, so you can see if you can try and fix that, because it will give you the most return for your time. So an example here, we have a view model, which is basically doing something with image data. We don't know what it is, but we do know that the flame graph is basically showing it as the largest function that we own. Step two of fixing an ANR would be to basically find where that is in the source code. So we have an example here, which is quite simplified, but we have a view model, which is doing some JSON serialization on the main thread, which seems fine, right? But in reality, like, this response model might be really complicated. It might be hundreds of kilobytes, for example. And lower end devices that have multiple other apps running might not be able to serialize that very fast. So you might be adding on perhaps seconds of time. So this is a simplified example of how to fix an ANR, but we could just, instead of running that on the UO thread, we could run that on a worker thread instead. And that would avoid having to have our main thread blocked. We could display some sort of intermediate progress UI, something like that. So I'd just like to recap a little bit there and go over the key takeaways from this presentation. ANRs can really impact your business and your organic search results. If you're above that 0.47% bad behavior threshold of ANRs, then you effectively don't get like featured in Google Play. You can't show up in organic search, and your users might just not have a good time using your app and not decide not to purchase or buy your app. We think that the existing tooling in the mobile ecosystem basically treats ANRs the same as crashes, which is probably a reasonable assumption starting out with deadlocks and for those ANRs where the main thread really is just blocked by one thing for a long time. But it doesn't really fit the model where you're doing a lot at the same time and you need to figure out what's happened throughout the duration of an ANR. I hope you've basically taken away from this that the framework monitors ANRs differently depending on which component they're in. So it's not as simple as an ANR always blocking the main thread from an ANR isn't always the main thread being blocked for 5 seconds. It can be different in different components, like broadcast receiver gets a slightly longer threshold, etc. And finally, I hope we've shown that having data for more than just the very end of ANR can basically help you figure out what's going on with ANRs in your app and give you the insight you need to actually fix those problems. So thanks very much for listening. If you have any questions, you can reach me at my email there. Also, if you want to learn more, feel free to take a look at embrace.io, because they basically got me here and sponsored my talk. And we also have a booth with a very fun Catch the Light game, which you might have seen already. Thanks very much.